All right, hi all, and welcome to the Medical AI Lab Reading Group. Every Thursday, a lab member covers a recent paper in either core AI or medical AI, and these sessions are targeted to be broadly interesting to those who are interested in the cutting edge of AI and its applications to medicine. This week, we have Xiaoli Yang discussing a paper called ZeroShot Transfer with Locked Image Text Tuning. And so without further ado, I'd like to welcome Xiaoli to share this paper with us.
Thank you so much, Pranav. Okay, I'll start present right now. Okay, it's thinking. Okay, so hello everyone, I'm Xiaoli, and it's pretty exciting to be the first to present this quarter. And today, as introduced by Pranav, I would like to share this paper on LiT. And not surprisingly or surprisingly is again from the Google research team. So if you have any questions or thoughts during the presentation, you can just interrupt me and we can all discuss together. And a spoiler alert is that this paper involves a lot of experiments and table results and graphs. So it'll be a bit dry if we go through them one by one. So if you find any interesting observations, just feel free to share with the team. And because the observation from only one person is not necessarily like exhaustive. Okay, so here we go. I structured my presentation into three main parts. First, we're going to briefly explain the problem LiT is going to tackle, which is zero-shot image classification. And then the image text towers. And this is an architecture that LiT is improved directly upon. And finally, we're going to dive into LiT and a series of experiments that comes along with it. So first of all, what is a zero-shot image classification? Zero-shot basically means we have zero training examples. When we need to classify a category during the test time, but our model has never seen it during the train time, then how can the model deal with it? So like this zebra, when we have a training set that consists of birds, horses, dogs, cats, and fish, like the model has no way to know that there exists something called a zebra. So if we classify this zebra with a supervised classifier, then it's definitely going to classify the zebra into one of the presented or predefined categories, or most likely to be one of the horses. So this is a problem we want to solve. And someone creative proposed an idea saying that, oh, probably we can use some auxiliary information that link the zebra and the image we have together without telling the model directly, oh, this is a zebra. So one way to do this is to use the image and text pairs. The main idea is that we can let the model to train from images that comes with very detailed text description, like an image with this caption. And somehow we can let the model to learn that it can translate or match the image with an appropriate pairs of words. And from those words, the model can guess that, oh, if we have a horse, it's an animal, and it comes with black and white stripes, then it's probably a zebra. So that's the main idea of zero-shot image classification. And then this leads to the prototype of our image text towers. So in this architecture, we have a text tower and an image tower. You can also say that they are text encoders or image encoders. I don't really know why they call this tower instead, but anyways, so they are text towers and image towers, and they both train simultaneously using the image text data pairs in the same embedding space. So we are going to train this using contrastive loss. That is, we want to drive similar text, similar images to have similar embeddings. And we also want the paired image and text to be close in the embedding space. The technical details like how contrastive loss works and its formula, we won't talk about them in this presentation as it's not part of the interest of LiT. Also, if you are really interested in the mathematical details, you can look up the paper by searching a line or clip. They have a very detailed set of like experiments as well as how they come up with the idea of using contrastive loss. So yeah, so after we train this text tower and image tower together using contrastive loss, we directly have a preliminary trained zero classifier. So we call this method of training two towers from scratch using image text pairs contrastive pre-training. It has both advantage and disadvantage. So the advantage is that with image text pairs, the model actually can train without predefined labels. This actually already combats the previous problem we encountered together. Like we are not limited by the labels like horses, fishes, and cats, dogs. We are going to classify based on natural languages, like a sentence or several free words. And second advantage is that it's quick and dirty. It's quick because the pre-trained text and image towers are already pretty effective zero classifier. So imagine that we want to classify based on a set of labels. We just directly pass in the labels as words and text, and the model is able to search for the embedding space around these like text embeddings to see which images are around. So and classify the correct images into correct bits. And yeah, and the dirty part comes with its weakness. The dirty part is that the image text data set is really noisy. And you can imagine because it's collected all over the place from the internet, from stock images. So if we directly use the image text pairs to train our image model, then we can expect that its embedding is not very high quality. So this could potentially hurt the model performance. And we want to find some way to combat this problem. Okay, so far, is there any questions? Okay, so with our prior method being contrastive pre-training, now the LiT team is proposing a small change to the original architecture, which they call contrastive tuning. So they remove the pre-training part by saying that, okay, since pre-training using the image text pairs directly is not that effective and could potentially decrease the performance, how about we just use the pre-trained models from image and text directly? Then we can basically enjoy the benefit from like really high quality image embeddings and text embeddings. And this is the general idea. And we have extra advantage that is like by removing the part of the, by moving the image text pairs into only the stage of contrastive tuning, we are actually decoupling all the tasks we are performing together. Like in the past, imagine that we actually have at least 3 tasks going parallelly. The first task is to train the image encoder. The second task, train the text encoder. And the third task is to find some way to align the correct image to the correct text. So there are 3 going parallelly, and it's pretty inefficient and complicated. And it's hard to do with only like noisy image text data pairs. However, by using the pre-trained image tower and text tower directly, we're actually freeing ourselves of 2 of the tasks. We do not need to worry about like training the image tower and text tower like directly. That's the pre-trained model part. And we only need to worry about tuning very good image text relationships during the contrastive tuning. So that's potentially one interpretation why contrastive tuning is effective in this way. Okay. So we are halfway through the like proposals that LiT team made. The contrastive tuning is the first proposal, and the second proposal they made is the design choices for LiT itself. So now with the pre-trained image and text towers during initialization, we can actually choose whether or not we use pre-trained model for both image or text tower, or whether we lock or unlock the weights during the fine-tuning step. So there are a few notations that we need to learn. The first one is capitalized letters and L and U. So we use capitalized letter to indicate whether we use the pre-trained model. So and we use L to indicate lock, U to indicate unlock. So putting them together, there are three possibilities. When we have capitalized L, that means we use pre-trained weights and we lock them. When we use capitalized U, we use pre-trained weights and unlock them. Small u is we randomize the initial weights and unlock. And here is another spoiler alert. So among all of these possible combination of designs, LiT actually refers to the design choice of we are going to lock the image pre-trained model, and we are going to randomly initialize the text tower and unlock. So when we talk about LiT in this following paper, we're explicitly referring to the big L and small u setup. And the authors has done a lot of experiments to show that this setup has been proven to work really well. Okay. Now we are going to proceed into experiments. So there are a lot of experiments they have performed, and they try to adjust each part of it, each component of it to show that it's the optimal. So we will quickly look at some components first. First, the author tests the LiT performance when training on different like public or private data set. So both CC12M and YFCC100M are public available benchmark. And some low quality images are filtered out in CC12M, and they eventually ended up with 10 million image data pairs. And also for the YFFCC100M, it's originally a multilingual data set. So they picked out only the English part and filtered some low quality images, and they call it CLIP dataset. And it's eventually 15 million image data pairs. And finally, they collect a huge dataset, which is like 4 billion pairs from all kinds of sources. And what they eventually use is around 3.6 billion. And I think it's quite astonishing that the public dataset is so small compared to the private dataset. But as we will see later, their performance on the image and ZeroShot classification is actually, I would say, comparable. At least not, the gap is not as huge as compared to their like size difference, which is, I think, very astonishing. That proves the LiT setup is really data efficient. And the second part is design choices. We already introduced this on the previous slide, so I won't spend more time. And thirdly, author used a series of evaluation dataset to test this performance. Here are, everybody knows the ImageNet dataset, which is like classical famous dataset. And there are also 5 out-of-domain variants of the ImageNet. So all of these 5 are like extra collected examples, but they share the same labels used by the image set. The first ImageNet version 2 is a set of additional text examples that are collected like separately, but as closely as following the ImageNet's collection protocol. And ImageNet R is a collection of artistic image like sculptures, paintings, etc. And ImageNet A, these are hard examples for ResNet 50. They collect a set of examples that ResNet 50 cannot classify correctly and put them into a set. And for ObjectNet is used for object detection as well as object orientation classification, something like that. And REAL is a set of examples that are reassessed for their labels accuracy, either put more accurate annotations or multi-labels. And finally, they also use a set of VTABN. These are a collection of natural data sets in order to test diverse downstream tasks. And finally, they compare their models to previous state-of-art models, mainly Clip and Align. They are both contrastive pre-training models, and they mainly perform experiments on zero-shot image classification and the image text retrieval. We put in query of the text and return the image, or we put in image and return the text query. Okay, any questions? Okay, now we are going to look at some results. The first one is LiT actually significantly outperforms all the previous state-of-art models. So for the first set of experiments, we will use image tower with G14, and we are going to randomly initialize text tower. So without specifying other words, it is said that the text tower architecture usually uses word base. And okay, so let's first focus on the experiments done using our constructive private dataset, which is like the first 3 lines. We can see that for the classification task on the ImageNet, the LiT tuning is achieving an astonishingly like 8% advantage over other previous state-of-arts. And also, if you look at the last line that represents the supervised baseline for ResNet 50, it also beats the supervised baseline by a large margin, almost 10%. And this is very, very impressive. And for some other out-of-domain tasks, it's also consistently stable and really well performed. Yeah, and for some stability tests in the downstream text is around 71% compared to the fully supervised 72.6. I would say like it's really stable and almost beating the ResNet 50. And finally, a quick result is all of the previous results are on our really huge private data set. But if we train our LiT tuning on our very small public data set, it's actually still achieving a very good result. But our previous model is not that stable, achieves only like 30% accuracy. But ours is still like even beating the ResNet 50 supervised baseline in the ImageNet version 2. So yeah, I just think that this is like really awesome. And next, LiT is also pretty stable when trained on the public available datasets by saving a lot of data computations. And this is the graph. Like notice on the graph on the left, when the LiT achieves 78% accuracy on the zero-shot transfer, which is like the leftmost point here, it only used 300 million image text data pairs, which is like 0.3 here. But it takes Clip at the same, roughly the same performance, like 76%. It says it takes like 13 or 14 billion pairs, which is like 40 times larger. So in order for our previous state of art to achieve similar performance, it requires much larger data sets. And so that's why we say like LiT is really efficient in data and computation. Any thoughts or interesting observations for the first set of experiments? No.
And this is quite interesting. I think one thing that this makes me think about is, so the image encoder and image tower isn't being modified at all, which means you're not learning sort of a different representation of the images. So if you wanted to improve that, those representations, those aren't improving. You're just improving their alignment with the text itself.
Right. That's really, I find that really like astonishing as well. Like if by any chance we can improve the model, like say by tuning the image tower further, then that means we may like spend extra amount of energy like trying to get that marginal performance. But it turns out, as the next set of experiments show, that even when we have a long tuning schedule, the logged image tower is still like optimal. So we wouldn't even need to worry about like fine tuning the image tower to get better performance. We just leave it logged, and we can even extract embeddings offline. So that is pretty cool. Okay, so as we say, we are going to proceed into this part, which is to test, to look at each experiment in detail. So in this set of experiments, the authors explore various combinations of locked and unlocked towers and show like how they eventually end up with choosing a locked image and unlocked text tower as their LiT setup. So one note before reading the curves is that these curves are trajectory. They are not training curves. So each point on this curve represents a single experiment. So as you can see, they run so many. And for example, the dot here represent that under the LU setting, if I limit the training steps to be 20,000, after I sweeping all the learning rates and weight decays and so on, I choose the best performance, the best experiment. And this is the accuracy, zero-shot accuracy I do ended up with. So in this way, the author tried their best to avoid misleading results by unthorough parameter tuning. So some quick observations here are, the first one is, if I lock the image tower, it almost always works the best for zero-shot classification. So if we see the comparison between the blue curve and the green curve here, there's a huge gap, nearly, I would say 10%. So it's also the same case for the validation loss, but not necessarily for the image and text retrieval. And the second is, using a pre-trained image tower significantly helps. So this can be seen by comparing the red, green, and blue curves. And the third one is, locking the text tower doesn't really help, because we can see like all the gray curves are clustering down here, and they do not end up with like increasing as the time passes. And another observation is, as I mentioned, in the image retrieval tasks, the difference between the green and blue curves are not that significant. So that indicates that there might be a limitation on our LiT performance. So if we, actually, according to the cluster, in very long tuning schedules and big U and small u, this setup sometimes overtakes the LiT setup on these tasks. So if there's a budget limit, we can choose LiT as our choice. But if we have extra money to spend, one may need to consider that using big U and small u, then we can achieve better results. Okay, no questions. We'll proceed. And notice that we have LiT performance that may vary according to tuning schedules, like the one mentioned just now. Then another question that one may ask is that, what will happen if I tune on a much larger data set? So right now our data set is relatively small, it's clipped 1 FCC, it's only around 50 M. But if we try on a huge data set, will that change the situation, saying that, oh, actually our locked image tower do not work as well? So next we are going to explore this. The authors perform a comparison between 3 design choices, and they conclude that even with large and general pre-training, LU is still doubtlessly the optimal model. So we won't worry about that situation at all. And this resolves the previous question. Is that okay? Okay. So next observation is that LiT tuning works better for more generally pre-trained models. And this arises because one may argue that LiT training only works because we initialize the model backbone with a pre-trained classifier. So it basically acts as a supervised classifier instead of a part of the real image text model. So if this argument were true, it will potentially mean that our model's generalization ability will be undermined, and its quality will largely depend on the quality of the pre-trained models. So that's not what we want. So the author designed another set of control experiments to combat this argument. So they basically pre-trained the models in a variety of ways, as shown here. We have IN represent the ImageNet, and IN21K represent the much larger version of ImageNet with 21,000 examples. And they also had a data set called places. It's really narrowly defined. It's only like various names of places of all over the world. And they want to show that more generalized trained models actually perform better after the LiT tuning, and LiT tuning tends to make like generally trained models more similar to each other. Okay, so let's look at the first set of experiment. In the first fully fine-tuned experiment, all models except for the places achieves around 77% of accuracy. So that means the first 5 models can be considered similarly good models, like before the LiT tuning or when we are doing the supervised tuning. And but with LiT tuning, the models that are trained more generally in the first 3 rows are marked green. That means they appear to be more similarly good. So although the supervised ArcReg on the ImageNet achieves like excellent performance on the ZeroShot classification, this is actually a misleading advantage because its generalization is optimal and its performance is really bad in other downstream tasks. So we can conclude that from this control experiment that as long as models are pre-trained generally, we will end up with similarly good results. And the more general, the better. This graph may consist of a lot of information. So if you are not sure of any part of it, just ask. Okay, so next question is, after seeing all this like performance and generalization of LiT, we're wondering like why it actually matters to choose the weight as the image model. So recall that unless otherwise specified, LiT is always going to use weight as the model and BERT as the underlying text model. So why is that a good choice? Will necessarily like will it fail if we just change another model? So the short answer is no. And the author experimented with weight with different sizes, as well as 2 other like completely different image architectures, and find that actually they perform, I would say, equally well, although weight is indeed usually the fastest as well as the most accurate one. So LiT has a really cool freedom for you to choose like image models and without affecting a lot of its performance. Okay, so next is after exploring the ideal image model, they also explored ideal text model to use. So they trained weight-based BERT along with other like transformer-based text models on the YFCC dataset and their large private dataset. So here the numbers are presented in accuracy with random initialized weight. So for 57.2 and 57.8, they are like all randomized initialized weights. And numbers in the brackets indicates the percentage increase by giving a pre-trained text model. So we can say that having a pre-trained text model consistently help, but only by a little bit. And a second interesting observation is that the BERT model performs much better than other models when trained on YFCC. Because since BERT is the only model that uses the word tokenizer, we are not really sure whether the increase in the performance is due to the BERT architecture by itself or due to the use of word tokenizer. So we perform an extra experiment letting weight to use word tokenizer as well, and end up seeing that, oh, it didn't achieve as well as the BERT with word tokenizer. So it's probably the magic lies within the BERT. But the author thinks like, oh, there are so many mechanisms in the BERT, and it's very likely that by chance the word just works. So they further tested BERT on the private large data set and find that actually its advantage does not stay under the large scale tuning. So they eventually decide that it's not worth it to use BERT anyways, because it's really hard to train and its performance is not stable. So their conclusion is that for the text model, the ideal model is still weight. So to summarize, the ideal image model is weight, but for others is equally performing well. But for the text model, the one that is most easily trained is still weight. Any questions so far? Okay, so, and next, we are exploring the effect of model size in prediction of performance. And for this task, we are evaluating the ZeroShot ImageNet classification. And we use the pre-trained weight models of various sizes and also the pre-trained BERT models as text towers. So we tried all possible combinations by varying the text as well as the image towers. The change by varying the image tower sizes is shown using different bars. And the change by the text towers from the BERT base, BERT large and BERT huge, are indicated by small increments at the top of each bar. So we can say that the main improvement in the performance is mostly brought by the size of the image tower. And although the text tower size does help, is like the increase is really marginal. And the help from the image tower size is really, really obvious, in particular when we increase from relatively small models. So if our resource is limited, the wise way is to increase the image tower instead of the text tower. And the seventh piece of information is we are exploring like whether or not duplicated examples in the upstream and downstream text matter for LiT tuning. We will worry about this because if duplicated examples do provide extra information in downstream tasks, then there's a risk for data leakage. And we need to spend extra effort to remove all those duplicates and to search across our data sets. But if it doesn't matter at all, then we will save the efforts of removing all duplicates. And a quick answer for this question is that it doesn't matter if we are tuning large scale. And to explain in detail is that the authors designed 3 sets of experiments. The first setup is they do not perform any deduplication. And the second one is they remove the duplication in the LiT tuning data with respect to the downstream test set. And the last one is they remove respect to both the train set and test set. So it's obvious to note that there's actually not a huge effect in like removing the duplicates at all. So one potential interpretation for this is that the model may not memorize those duplicate examples because we just have too many data. So in the real training cases, we don't need to worry too much about removing the duplicates. That saves a lot of power. But in this paper, our experiment setup follow the strict deduplication protocol to avoid like any possibility of data leakage. And a last piece of information is the author also did some preliminary multilingual experiment to explore the model's potential in predicting in foreign languages, not just English. So they used the weight B32 for image tower and tried both the text towers in T5 and MT5. And in order to compute like LiT's performance in English versus the non-English, they trained the LiT on the YFCC clipped. Recall that YFCC clipped are only in English. And they also trained the models on the whole YFCC dataset that is like multilingual. And also to prepare, they translated the ImageNet prompts into common languages using online translator. So ImageNet prompts are small sentence fragments, like instead of only passing in the class name, they're saying that a picture of horse or a sculpture of woman, like that. So they translated that into common languages and used that to perform zero-shot classification. And they end up finding that with the augmented multilingual data set, the English performance is not affected at all, but even improved. But for other languages like non-Latin languages, they gain a huge performance improvement. And so this is potentially very interesting because notice that, for example, for Japanese or for this ES, is obviously by this observational performance is not one of the Latin language, but even with only English data pairs, it still achieves around 20% by entering a foreign language, which is not Latin. I think this is pretty surprising. And 20% is definitely higher than random guessing for hundreds of thousands of classes. Okay, so in summary, the authors are proposing that, okay, the LiT is really potentially powerful in coming up with high quality image classification in the future for languages that has low resources in text descriptions or captions, etc. So this could be a future research direction, and LiT can be a really powerful candidate in this path.
Sorry, Xiaoli, can I ask a question here? So I just want to make sure I understand this figure. So what is the pattern indicate on the graph?
Okay, so on the graph, the shaded areas are accuracies achieved using only the small clip subset, which is around 50 million in English only. And these solid parts are achieved by the full set, consisting all kinds of languages. And they are saying that incorporating the more language in our contrastive tuning step doesn't necessarily interfere or decrease the performance of our English when we query using our English language. But for other languages like non-Latin languages, when they are trained only using English captions, they gain only 20% accuracy. But if we incorporate all kinds of language, not necessarily its own, there's a huge boost. So basically that's the information. So the authors are saying that this could potentially be really useful if we have a limited resource in one language. For example, if we have a very rare language, but if we augment it with other kinds of language, although not itself, it could potentially be really helpful.
So let me try to just interpret some of this graph, and you can tell me if my interpretation is right. So taking a non-Latin language, let's take Japanese. So on Japanese, what it's seeing is using the T5 model without multilingual, you're basically near zero, but with multilingual, you're at 20% with the full data. And the shaded portion is just saying using a smaller subset, I would have gotten similar boosts.
Yes.
Okay, got it. While for Latin languages like Spanish, French, we're seeing the difference between the multilingual and the normal T5 not being that much because the blue and the orange are the same height.
Yes, that's right.
Okay, all right, cool. Thanks, appreciate it.
No problem. Okay. And finally, we are back at the observations, and there are a lot of observations we've made, and here's a summary of it. Finally, we get to our summary stage. So basically, we look at the LiT architecture, and we found that it's a really well-performing model, and that can save a lot of computation resources as well as data resources, and they are very effective zero classifiers. And also by locking the image tower, we can like save time and computation by like avoiding computing gradients or something like that every time. So we can easily like save the embeddings and reuse always. And it also has some limitations, as we mentioned before, in some long tuning schedules and under certain tasks, our LiT architecture is not necessarily always the optimal choice. And there are better choices that you can spend more time to explore. But if we are under a time budget or a cost budget, LU is always the safe choice to use. And also, this paper only explored zero-shot classification as well as the image text retrieval tasks. There are more tasks awaiting us to try. So that could be one of our future directions. So thank you very much for all of your time. And also here is some of my own notes. Okay, I think that's the end of the presentation. The rest
Awesome.
is like for the new students.
Excellent. Thanks a lot, Xiaoli, for the great presentation. Thank you.